Hello everyone. So we move on with the last video for lecture 2, and we will be talking about cryptographic hash functions and how we can use them to ensure communication integrity. Now keep in mind that cryptographic hash functions, could take, if someone wants to explain them in details, it can take up many lectures, right? Nevertheless, in our case, we just want to describe the main properties and how we can use them in order to provide integrity protection on the exchange messages in a communication protocol. Right. So I hope you all remember the example with the login form that we described in lecture 1. So we have a typical login form. We have Alice and Bob. I hope you did not forget that Bob is playing the role of the server here. And then Alice, who wishes to log into her mail, for example, she types her username and password in the corresponding fields in the login form, and then by pressing the login button, a message is generated that is sent to Bob. Now this message contains basically Alice's credentials, Alice and ABC1, 2, 3 in this case. Now we said that if we assume that we have Eve in the middle, that she is over here in the communication between Alice and Bob, she can basically see the password of and username of Alice. We don't care about the username that much because it's anyhow public information. But anyway, if you also have access to the password, then Eve can impersonate Alice. Now, in the previous video, we described how public key cryptography works. So the question here is, can we use public key crypto to help us here to solve this problem, basically to protect Alice's password? So I would like you to take, to pause the video here and just take some minutes to think about it. Okay. Right. So usually what someone would obviously think is that what we can use is that Alice can use Bob's public key. Bob's public key is known to everyone, is public information, okay, and by having access to Bob's public key, it doesn't say anything about Bob's private key. So Alice, she gets access to Bob's public key, and she is using this to encrypt her credential. So basically, instead of sending her username and password in plain text, as in the previous step, she will be using Bob's public key to encrypt that message and send the encrypted version of the message to Bob. Now, upon reception, Bob, who has access to who is the only one who has access to his private key, he uses his private key to decrypt the message and get access to both Alice's username and password. Now, this is a very bad technique. Why? So again, please pause the video a bit and try to think about it on your own. Now, why this is a very bad technique? It's because if we do so, if we encrypt all of our private information with Bob's public key, it's like we assuming that Bob will be always trusted, right? So giving out our password to Bob is not a good strategy, right? We must make sure that our password will never be known to anyone else but us, the actual password, right? So imagine in a case where Bob, at some point, he gets compromised, okay? So basically, Bob has access, knows all the password of all users, right, that he has stored in his database. Now, if Bob has been compromised, then immediately the hackers that compromised Bob's server can impersonate millions or thousands of users, right? And that's bad. So let's see how cryptographic hash functions can help us in such problems. Now, cryptographic hash functions provide data integrity and message authentication. So the general idea is that the cryptographic hash function, denoted as H, is a hash function which is considered impossible to invert, which means that given H of 1, which is equal to the hash of m, h of m, it should be impossible to compute an inverse function. An inverse function, which means that it will take as input the hash of m and it will be able to recover m. So that's the general idea of a cryptographic hash function. Now, a cryptographic hash function is similar to a checksum. The main difference is that while a checksum is designed to detect accidental alterations in data, a cryptographic hash function is designed to detect deliberate alterations. When data is processed by a cryptographic hash function, a small string of bits known as a hash is generated. Now, the slightest change to the message typically makes a large change in the resulting hash. Apart from that, the cryptographic hash function h is a function which takes arbitrary length bit strings as input and produces a fixed length bit strings as output. It doesn't matter how big the input is, the output will be always the same. Now, the output is often called a digest or hash code or a hash value. Hash functions are used a lot in computer science, but the crucial difference between a standard hash function and a cryptographic one is that the cryptographic hash function should at least have the property of being one way. In other words, given any string y from the codomain of h, which means the hash of m, it should be computationally infeasible to find any value x in the codomain of h, such that h of x equals to y. Now, two important properties of cryptographic hash functions: they can be used to compress a message. We will see this in the next lecture about digital signatures, and they are easy to compute. So it's very easy to compute the hash of m. It doesn't take much time. It doesn't need many computational resources and so on. Now, let's see some more core properties of cryptographic hash functions. So given the hash function h from x to y, we say that h has pre-image resistance, or known as one way, if it should be hard to find the message with a given hash value, which means that if you are given y, it should be computationally infeasible to find the value x such that h of x equals to y. In addition to that, it should be second pre-image resistance, also known as the weak collision resistance. This property says that given one message, it should be hard to find another message with the same hash value. Okay, so if you are given x, it is computationally infeasible to find another value, x prime, different than x, different than the original value, such that the two hashes are equal. And finally, we have the collision resistance, which is known also as the strong collision resistance property, which says that it should be hard to find two messages with the same hash value. Obviously, assuming a function h is pre-image resistance for every element of the range of h is a weaker assumption than assuming that it is either collision resistant or second pre-image resistant, and assuming a function is second pre-image resistant is a weaker assumption than assuming it is collision resistant. These are two kind of theorems, and there's two nice proofs if you look at the crypto textbook. Now, we will end this part of describing in a very high level cryptographic hash functions by giving a final remark on how we should think about the security of unkeyed hash functions. Just a comment here before I move on. So what we describe here is known as unkeyed hash function, which means that we have a function that takes as input only a message m, okay, and not a key. These are called unkeyed hash functions. As we will see in the next lecture, there are also what we call keyed hash functions, which take as input a message m as well as a secret key k. Now, so let's give a final remark on how we should think basically about the security of unkeyed hash function. So the method adopted in much of the practical cryptography um, is to assume that an unkeyed hash function acts like a truly random function, and that um, despite basically despite the fact that the adversary having the code of H. So we assume that if the adversary knows exactly how the hash function works and all of its specifications, so this acts like a random oracle. In practice, we define our cryptographic schemes and protocols assuming a random oracle and then replace the random oracle in the real protocol by a fixed hash function. So while this is not a perfect methodology, it does work in most instances and results in relatively simple final schemes and protocols. Good, so now let's go back to our login form. So again, the same scenario, we have Alice and Bob. Alice wishes to log into Bob's server. So she types in her username and password. By pressing the login button, she sends a message to Bob. Now, how we are going to use hash function to protect our password, instead of sending the password in plain text or encrypted with Bob's public key, we will just calculate the hash of the password. Now, upon reception, Bob will check first of all in his local database if there is a user with the username Alice. If there is such a user, then he will check the table with the stored hashes of the passwords that he maintains in his local database, and he will check if the hash for that user that he has stored in his database is equal with the hash that was sent by Alice. If the two hashes are equal, then it means that Alice knows the password, so probably she's a legitimate user, and therefore Bob will give her access to the servers. Good. So what do we gain here? Basically, even if Bob gets compromised, okay, he will not be able to find the exact password that Alice is using. This is because, as we said earlier, one of the main properties of cryptographic hash functions is that they are invertible. So knowing the hash of ABC123 cannot take you back to the actual password. Okay, so Bob cannot reverse the hash of Alice's password. Now, some popular cryptographic hash functions that are widely used is SA512, SA1, SA3, and MD5. So if you build a web application now, or anyway any kind of application, and you must use a hash function for something, do not use MD5, do not use SA1 or SA512, just stick to the latest SA3. Good. Now the road towards integrity. So in this slide, I'm going to give a very simple and basically bad example of how we can use cryptographic hash functions to provide integrity to our communication. Nevertheless, despite the fact that this example is bad, I mean, it has a lot of flaws, I think it's a good start to get the main idea. Okay. So again, we have Alice and Bob. So Alice sends a message to Bob. We don't care about privacy now. Now imagine that we have Eve in the middle. What she can do is that basically she can intercept the message M that Alice is sending, and she can drop it and replace it with a fake message M of Eve. Now, Bob, upon reception, doesn't have any way to check that someone altered that message, right? So basically, he doesn't have any way to check the integrity of the message, right? And once he receives the altered message, the fake message, he will think that this message was written by Alice, which is not the case. Now, imagine that if we can use a cryptographic hash function, instead of just sending M, Alice will send M plus H of M. Upon reception, Bob, what will do is that he will have to calculate on his own the hash of M and then check his own result with the hash that was sent by Alice. If the two hashes are equal, then it means that the message has not been altered. Okay, and then Bob will treat the message as it was really sent by Alice. Now, as I said earlier, this is a really bad example. It has a lot of flaws. It's very easy. I mean, you can find many ways of fooling Bob in this kind of protocol flow. But the main idea is, my point here is that you get the main idea of how we will start using hash functions in order to protect the integrity of our messages. You will see more details in lectures 4 and 5, where we will start constructing real protocols and protecting the integrity of the messages. Good, so that was it. With this video, basically, we complete lecture 2, and then in the next lecture, we'll start talking about digital signatures and digital certificates. Thanks a lot. Bye.